Hello everyone. Welcome car students. I appreciate if you check in by writing your name and sending it to me in the comments so I see who's attending. So I'll be holding class every day at this time on weekdays. If you have any questions, let me know, especially over the weekend. That way it gives me some time to prepare and answer some questions for you, prepare some materials. Today we're going to talk about we're going to review the Lewis structures that I taught you before we took the March break. And then I will also start going into Vesper theory. I'm going to give you some notes on Vesper theory, and then we'll do some examples. So with Lewis structures, you recall that the first thing you have to do is make an accounting of how many valence electrons are in the molecule. You also have to account for the extra electrons or the deficit of electrons that occurs when you have a charge. If you have a negative charge on the anion, then you have extra electrons that have to be tacked on to the tally for the number of electrons that are involved in bonding. If you have a positive charge, then you subtract them. So I'll do a couple of examples just to show you how that works. I'm thinking I'll do the iodate series, and I'll do ammonium for you just to show you an example. I'll start with ammonium because it's an easy one. So ammonium is NH4+. So what I recommend before you do any Lewis structure is draw yourself a T-chart. Put atom on the left, number of valence electrons on the right. Then you list all the atoms involved in the molecule, and then put E- to account for extra electrons or for a deficit of electrons due to charge. So nitrogen has 5 valence electrons. Hydrogen has 1 valence electron, and there are 4 hydrogens in the molecule, and you're missing 1 electron because the molecule has a +1 charge, so we're going to subtract 1 electron. So the total number of electrons in ammonium is 8. 5 plus 4, 9, minus 1 gives you 8. So 8 electrons have to be accounted for in the structure of ammonium. We draw the central atom, which is nitrogen in this case, and then attach the 4 hydrogen atoms to it. Remember, we're not really making any statements about the geometry of the molecule yet. That's in chapter 9. That's Vesper theory. All we're saying is where are the bonding electrons, or how many of them are involved. So there's 8 of them there. Each of these lines counts for 2 electrons. So it's 2, 4, 6, 8. So a nitrogen has an octet. Nitrogen normally wants to have possession of 5 electrons, but in this case it only has full possession of 4 electrons. So in actual fact, the nitrogen atom has a positive charge in ammonium, and that's fine because the ammonium cation should have a plus charge, a +1 charge. So that's ammonium for you. Let's try periodate. Periodate is IO4 with a -1 charge. So let's draw our T-chart. Number of valence electrons. Iodine, or iodine rather, has 7 electrons in it. Oxygen has 6 valence electrons. There are 4 oxygens in the periodate. And finally, there's a negative charge of 1, so we're going to add 1 more electron to account for that formal charge. So 6 times 4 is 24, plus 8 gives you a total of 32 electrons to account for. We're going to put the iodine atom in the middle, and we're going to attach the 4 oxygens to the central atom. Then we're going to use up all those valence electrons by giving octets to each one of the individual oxygen atoms. And that uses up 24 electrons. 6 times 4 is 24, 26, 28, 30, 32. So we've used up all 32 electrons. And if you draw it this way, you're going to have a formal charge on each and every oxygen atom. Why is that? Well, oxygen wants to have 7 valence electrons, but the way it's drawn here, it's got 2, 4, 6. Each one of the lone pairs counts for 2, and then this bonding pair counts for 1. So it's got 2, 4, 6 plus 1. It's got 7. Sorry, oxygen wants 6, and it's got 7. Because it wants 6 valence electron, full possession, but it has 7, each one of the oxygens has a -1 charge. Iodine, being a halogen, likes to have full possession of 7 electrons, but in this situation, it's only got full possession of 4, because with bonding pairs, it only counts for 1. So you've got 1, 2, 3, 4, and it wants 7, so it means that there's a deficit of 3. So the way it's drawn, this Lewis structure, the iodine atom would have a +3 charge. So what we're going to do is redraw the structure and redistribute the lone pairs so that they're shared between oxygen and iodine. And we can redraw the structure now, and it's going to look like this. You're still going to have one that is drawn with a single bond, but you're going to have a bunch of double bonds. Now that doesn't mean, and this is a bit of it's a limitation of this technique. It doesn't mean that we have all 3 double bonds and 1 single bond. What it really means is that you have 7 bonds shared over 4 positions. So the bond character of this molecule is 7 over 4. Because the electrons, they don't stay still. You can imagine them as having more like a wave function. They're moving so rapidly within the area of this molecule, close to 2/3 the speed of light, that really what you're doing is time sharing the electrons in that area. So what you really have is a 7 bonds, 2, 4, 6, plus 1, 7, shared over 4 positions. Traditionally, they've shown it as canonical structures where they show, a double bond here, a single bond there, double bond, and they show the single bond alternating in various positions. That's just a way of showing that the molecule is not static. So that would be the periodate anion as portrayed by Lewis structures. Let's now look at the beginning of chapter 9, which talks about the geometry of the molecules. Now, molecules are not flat like we draw them on a piece of paper. They actually have a 3-dimensional shape. And Vesper theory attempts to account for the fact that electrons repel each other. They're negatively charged. Think of them as negatively charged particles. They repel each other. They don't like to be in the same area of space. And they've discovered through calculations early on, when they were trying to discover the geometry of molecules, that the wave function of an electron is such that its energy goes higher if you try to put too many electrons in the same spot. So the reflection of this is that put in a nutshell by Pauli's exclusion principle, which basically states that no 2 electrons within the same molecule can have the same 4 quantum numbers, because that would mean that the electrons are occupying the same space within the molecule. So the electrons repel each other, and the maximum number of electrons you can get within one region of space within the atom is 2. And at that, they have to be spin paired. One has to be spin up, the other one has to be spin down, to reduce the repulsions between them enough so that they can occupy the same area in space. So let's just go over the 5 basic shapes. This is chapter 9. This is from chapter 9 of your textbook. If you want, you can follow along by looking at figure 1 in the textbook. In figure 1, it shows you the tetrahedral geometry. And tetrahedral geometry is the way carbon atoms typically bond. They'll have 4 bonds going to them. For example, methane, you'll have a hydrogen atom going up, one also going sideways in the plane of the blackboard. You can look at it that way. One coming forward at you, and one going behind the plane of the blackboard. If you were to look at the bond angles between all of them, it would be 109.5 degrees. And why that peculiar number? Why 109.5? What's so special about 109.5? Well, imagine an orange, and you have 4 toothpicks, and somebody says to you, I want you to stick these 4 toothpicks on the orange in such a way that they're as far apart as possible. If you succeed in your quest, you will find that the furthest apart that you could put 4 toothpicks on an orange, if you were to draw lines continuing away from the toothpicks and then continue those lines to the center of the orange, you would find that the bond angle that they create is 109.5 degrees. You can draw a tetrahedron by using a trick that I like to use. If you draw a cube, and the way you draw a cube is start by drawing a square. This works a lot better if you use a ruler. Then at the center of the first square, you draw the edge of a second square of the same size. And you connect all the corners, and that's how you draw a cube. Now, in that cube, you can pretend that you put a carbon atom, like the atom of a methane molecule, and then you draw circles on opposite diagonals on the top plane, and then switch 90 degrees and draw circles on the bottom diagonals of the opposite plane. And then you can connect the central carbon atom to the atoms that are at the apex of the cube, of each part of the cube. And you will, by doing this, generate a tetrahedral geometry. And it's hard to do if you don't use the cube, I find. I'm not particularly artistic, so that's a trick that works for me. If you do that, all these bond angles are going to be 109.5, and in fact, I teach my classes how to prove that these bond angles are 109.5. That's kind of an AP question, but we're not going to get into that today. That's just a trick you can use for drawing a tetrahedral point group, which is frequently what the shape that carbon atoms take. But let's explore the possibilities. In figure 9.2, they show you all the different shapes that the molecules will take. And in figure 9.3 of your textbook, you will see that they also put the names for the various shapes. So let me show you what those look like. If you have 2 things stuck to a central atom, the furthest apart they can be is 180 degrees. And that would be a linear geometry. If 3 things are stuck on the central atom, the furthest apart they can be is 120 degrees. And that's called a trigonal planar geometry. If you stick 4 things, as I showed you already, you get a tetrahedral geometry. And I find the best way to draw that is to draw 2 in the plane of the board, and then you make a fat triangular wedge coming at you. That's for the one that's coming towards you, and then you use hash marks to show the one that's going behind the plane of the blackboard. So basically 2 are like this, and 2 are like that. So this one is the one that's coming out at you. This one is the one that's going behind the plane. So 2 like that, 2 like that. And that's called a tetrahedral geometry. And the bond angle is always very close to 109.5. You'll see that it doesn't always go exactly to 109.5. There are molecules that have sort of a tetrahedral archetype, but they're not actually called tetrahedral because you can only see the bonding pairs when you use the methods that they use in chemistry to find the geometry of molecules. They use X-ray crystallography And they take pictures using X-rays because only X-rays have a short enough wavelength to make pictures of molecules that are discernible in any way. Then, if you have 5 things stuck on the central atom, you'll have one going up, one going down, one going sideways, one coming out at you, and one going behind. So the bond angle between these two is 120, and between these two it's 90, and this is called trigonal bipyramidal geometry. So 5 things. So you see 2, 3, 4, 5 things stuck on the central atom. The last one is when you have, I can do that on the top without erasing, when you have 6 things stuck on the central atom. Probably the best way to draw that is to have 2 coming out at you on the equatorial plane, and then 2 going out behind using the hash marks. Again, I apologize for my poor artistry. The bond angles are all 90, so no matter how you turn this molecule, the bond angle is 90 degrees between all the bonding pairs. And this is called octahedral, which you might find that mystifying. How can you have 6 things and you call it octahedral? Well, because if you were to stick this in the center of a cube, it would touch the edges of the cube and the top faces of the cube. And if you were to connect all these bonds, you would get effectively 2 square-based pyramids bottom to bottom, which would give you 8 faces. Okay, so that's where you get the name octahedral from. These are not actual bonds. I'm just drawing these to give you perspective. The actual bonds are the ones that are there. Okay, so that's 90 degrees. All right, so if you go to figure 9.4 in your text, you're going to see that you can have variations on these archetypes, these 5 archetypes, and I'll give you the example here. You can have, for example, a straight up tetrahedral. If you have methane, for example, it is a tetrahedral shape. So this is the carbon atom, and your hydrogen atoms are going to be there. One coming out at you, and one going behind the plane of the blackboard. If you were to look at the geometry of ammonia, which by the way has a lone pair on the nitrogen atom, the nitrogen atom is the central atom, and again it's got a tetrahedral archetype, but you don't see that lone pair, although it's still there. Okay, so you could draw the 2 hydrogen atoms like that, and then let's make the lone pair come out at you. So lone pairs are pretty big. They occupy quite a lot of space around the central atom. And then the other hydrogen atom is also there, going behind the plane of the blackboard. Now, because that lone pair occupies more space, it tends to push these down a little bit. So the actual bond angle here tends to be around 107 instead of 109.5. And if you look at water, water has 2 lone pairs on the oxygen atom. Then, again, the central atom is oxygen. And you have hydrogen, again, in the same positions. And you'll have 1 lone pair coming out at you and 1 going behind the plane of the board. They're taking up quite a lot of room because they're only held on one side by the oxygen atom. And they tend to actually pinch that bond angle down even more. It tends to be around 104.5 in water. So you see there's a bit of distortion going on as you get more and more lone pairs. And that's mentioned in page 347 of your text. Now what you should memorize are pages 351 and 354 on your textbooks. It shows you a chart of all the different shapes that you get with molecules based on how many lone pairs and bonding pairs that you have within the molecule. So it's up to you to read that chapter. It's really not the best place for me to write all these notes. Also, I do have a bunch of videos dealing specifically with VSEPR theory. So watch those videos. You have all the notes put there from years past, and it's done properly, a lot better than I could do on this little board. So do watch those in the next few days if you're interested in your chemistry education. I'm seeing there's only one person online right now. I wonder who that is. Is it somebody in my class? Or is it my wife?
No.
Not even my wife cares. Look at that. Anyway, this is for you guys. So take the time, because you'll benefit from it in the long run. I know nobody's putting pressure on you. I'll put a little bit of pressure on you. This is important because taking coronavirus is not only capable of damaging your health, it can damage your intellectual development. You got to take charge, okay? You got to take charge of your own life. Let's do a couple of examples. I'll show you how the, what pages did I say to memorize? Okay, 351. And 354. So memorize the chart on pages 351 and 354. That's basically what you're going to be tested on. So after that, it's all about, hey Rebecca, it's all about just going through the rules and drawing the molecule. I'll show you an example of how it works, and you'll see it's pretty easy, but you got to memorize that chart, those two charts, 351 and 354. Let's draw a structure for the chlorate series. So the chlorate series, we'll start with chloride. That's not going to have any geometry because it's just a bunch of electrons around one atom. But you have hypochlorite. That's going to be linear because it's only two, so we're not going to bother with that either. But we have, so it's hypochlorite, chlorite, chlorate, and perchlorate. So we'll focus on these three because they actually have some geometry that's going to be interesting. Let's start with perchlorate. So perchlorate is ClO4. So every VSEPR theory drawing, every time you want to get the geometry of a molecule, you got to start with your Lewis structure. That's why you got to master Lewis structures, which appear on chapter 8, so that you can then do chapter 9 properly. So I'm going to start by drawing the Lewis structure. Chlorine has 7, oxygen has 4. There's 4 oxygens in perchlorate. And then you have a negative charge, so add another one. So there are 16 plus 8, 24 electrons have to be accounted for in the Lewis structure of perchlorate. So perchlorate is going to have this kind of setup. Use up all the electrons by putting them on, by filling the octets on the satellite oxygen atoms there. So that uses 6 times 4 is 24. I did something wrong. Yeah, there's, sorry about that. There's 6 electrons in each oxygen atom, so it's 24 plus 8. It's 32. Okay, problem fixed. So 6 times 4 is 24, 26, 28, 30, 32 electrons it's accounted for. That's not the actual final shape, because if I draw it this way, the chlorine's going to have a formal charge of +3, and each one of the oxygen atoms is going to be -1. As it turns out, there's double bond character in there. One of the lone pairs get shared. And chlorine is capable of accommodating expanded octets. So that gets rid of all the extra formal charges if you do that. And you still have a formal charge of -1 for the whole molecule. So now you've got 1, 2, 3, 4 domains in there. There's 4 domains on chlorine. 4 domains means there's 4 areas where you have electrons. 4 domains points pretty conclusively towards a tetrahedral geometry. So perchlorate is going to have a tetrahedral geometry, and you would it would be it's kind of tricky to portray because how do you show double bonds with a tetrahedral geometry? What I like to do is I draw 2 of them, as many of them as I can in the plane of the blackboard, and then there's one coming out at you. So I'll put a square on that one like that, a triangle on it, and put the oxygen atom on the end of it to portray it. And then this one's going to be going behind. Okay, so that's your tetrahedral geometry with a 109.5 bond angle. And of course the molecule is polar because it's got a formal charge of -1. Let's look at chlorate. Myself some room here. So chlorate, ClO3 minus. Start off by drawing the Lewis structure. It's got chlorine, it's got oxygen, and it's got extra electrons. So there's 7 electrons in chlorine. There's 6 electrons in oxygen, and there are 3 oxygen atoms in chlorate. And then there's an extra electron to account for the fact that there's a negative charge overall. So 3 times 6 is 18, plus 8 gives you a total of 26 electrons to account for in chlorate. So I'll start by drawing chlorine as the central atom, and then stick on 3 oxygens, and then disperse all the extra electrons by filling the octets on the oxygen atom. That would give a formal charge to each oxygen atom, and it would give a formal charge of plus. Chlorine wants to have possession of 7 electrons, but in this case it has possession, I forgot one lone pair. Let's do the accounting. 3 times 6 is 18, 20, 22, 24. You got 2 more electrons, so you put them on the central atom. All right, so the way I've drawn it, each oxygen has a formal charge of -1. Chlorine wants to have possession of 7 electrons, but in this configuration it's only got 5, so that means it's going to have a +2 charge. We can further improve the Lewis structure by sharing lone pairs. So that would modify the Lewis structure to look like this, which is probably closer to life, to the truth. And you would still have a formal charge of -1, but now you have 5 bonds shared over 3 positions. So that's a 5/3 bond character. Now, because there are 3 bonding domains and 1 non-bonding, so you have 3 bonding pairs, 1 lone pair, that's still 4 domains. That's a total of 4 domains. So that points to a tetrahedral archetype, but you don't see that lone pair. So when a tetrahedral shape is lacking an electron, they call it pyramidal. When a tetrahedral shape is lacking one of the bonding pairs, they no longer call it a tetrahedral, they call it a pyramidal shape. And I guess the best way to illustrate that is to draw the chlorine atom as a central atom, and all the oxygen atoms can be drawn as though they were the legs of a stool. So there's 2 legs out. One's in the plane of the board, one is coming out at you, and one is going behind. So those are the legs of the stool. And then you could draw the lone pair pointing straight up. And the bond angle here would be roughly 107. Okay, so that's a pyramidal geometry. Let's try now chlorite. Still only one person online. Chlorite also has a -1 charge. Chlorine has 7 electrons, oxygen has 6. There's 2 of them in chlorite, and then there's 1 more electron to account for the formal charge, 12 plus 8, 20 electrons to account for in the Lewis structure. So let's start by drawing the oxygen atoms up and down like that, and then disperse electrons so as to fill the octets on the oxygen atoms. So that uses up 6 times 2, 12, 14, 16, 18, 20. That uses up all the electrons in our Lewis structure. So you have 2 bonding pairs and 2 lone pairs. I can further improve the Lewis structure by, because if I draw it this way, the chlorine is going to have a plus charge. It wants full possession of 7 electrons, and the way it's drawn here, it's got 2, 4, 5, 6, so it's 1 short of what it wants, so it's going to have a plus charge. The oxygens want possession of 6, they actually have possession of 7 this way. So what we can do to remedy the number of formal charges is share 1 lone pair, and then the molecule will, Lewis structure will be like this. You still have a -1 charge, which is what you want, and you still have 2 domains. So 2 domains, that are bonding, and 2 that are non-bonding. So 2 lone pairs, 2 bonding pairs. That's still 4 domains. So that's a tetrahedral archetype. But when you have 2 lone pairs and 2 bonding, it's not called tetrahedral anymore. You call it bent, because basically what you see is 2 bonds, but because of the presence of these lone pairs, they're bent down, and the bond angle here is going to be around 104.5. I didn't draw it that way, but I could redraw it with the proper configuration, so it'll look something like this. So you'll get something like that, and then the lone pairs will be 1 coming out at you, like that, and 1 going behind. Okay? And that would be a bent geometry. There's a couple more I want to share with you, and then that'll be enough for today. On practice example, on page 355. Practice exercise on page 355, it says predict the electron domain geometry and molecular geometry of chlorine trifluoride and the iodine with 4 chlorines, I don't know what it's called, ICl4 with a negative charge. Mama, you want to go outside? He was being very polite, but he was staring at the patio door, so I guess he wanted to go outside, and he did. Well, let's do 2 examples, and that'll wrap it up for today. So, practice example on page 356. Is ClF3 is the first example. So ClF3. So draw your T-chart. Chlorine always wants to have 7 electrons, same with fluorine, and there's 3 of them here. So you need 28 electrons to be accounted for in that structure. We'll start by drawing the Lewis structure. And you disperse the electrons to give octets to each of the atoms. 3 times 6 gives you 18, 20, 22, 24. You got to disperse 4 more electrons, so we'll put them on the central atom. Okay, so everything has an octet. Chlorine has an expanded octet. Chlorine wants to have possession of 7 electrons, and in fact has 2, 4, 5, 6, 7. So nothing has any formal charges. All the octets are satisfied. So the Lewis structure is satisfactorily drawn. You have 3 bonding pairs, 2 lone pairs, and if you look at your chart, the one that you're supposed to memorize, that's 5 domains. When you have 5 domains, that's going to give you a trigonal, bipyramidal, geometry. So when you draw that, you would, I just forgot to mention one rule, but you'll see it when you read up on it. Whenever you have lone pairs don't like to be anywhere close to each other. So if they're given the choice between having a 90-degree angle or a 120-degree angle, they'll take the 120. So the only way you're going to get two lone pairs to be at a 120-degree angle is if they're both on the equatorial plane. So they're like the skirt that the molecule is wearing. So whenever you have electrons, you're always going to find them in the configuration that maximizes the bond angle between them. So in the way you're going to draw this to do that is let me just double check that. Yeah, it's T-shaped. Yeah, so what you get is one fluorine going above the plane, one going below the plane, one going to the side, so you get the T shape. And then you get a lone pair coming out at you. And you get one going behind the plane of the blackboard, or the whiteboard. So it looks like that. So the bond angles at the equatorial plane, which means they're here. There's one sticking out like that, one sticking out like that, and one going behind. And then there's fluorine up and fluorine down. The bond angle here is 120. Okay, and they call that T-shaped. And that's what you get when you have 5 domains, but 2 lone pairs. Okay? The other example is ICl4 with a -1 charge. How much time we're hitting? 37 minutes. I'll probably cut out around 45 minutes. So ICl4 minus here's iodine, here's chlorine. Iodine likes to have 7 electrons. Chlorine also likes to have 7 electrons in its valence shell. How do I know this, by the way? Look on your periodic table. The group that the atom is in will tell you the number of valence electrons that it likes to have. So if you have 4 chlorine atoms, you're going to have that. So 5 times 7 gives you 35 plus an extra charge for the electron. It's a total of 36 electrons that have to be accounted for. So you're going to draw your iodine atom in the middle and your 4 chlorine atoms as satellites. Fill the octets of the chlorine atoms. Okay, so that's 4 times 6 is 24, 26, 28, 30, 32, 34, 36. Okay, all of the atoms have octets. Iodine has an expanded octet, and there's no formal charges. Iodine wants to have possession of 7 electrons, and you have 2, 4, 5, 6, 7, 8. There is a formal charge, sorry. Iodine has a -1 charge. And the ion is supposed to have a -1 charge. So that's fine. Everything is fine. What we have here is 4 bonding pairs and 2 lone pairs. That is a octahedral archetype, but it's not called octahedral. When you have 2 lone pairs, the 2 lone pairs try to be as far apart as possible. The only way that happens is by having them one up and one down in this case, because if you put them in any other configuration, they end up being at a 90-degree angle to each other, and that's a no-no for lone pairs. So what you get here is square pyramidal. Square pyramidal geometry means you have the iodine atom central, you have a lone pair going straight up, you have a lone pair going straight down, and then you have 2 chlorine atoms coming out at you, and 2 going behind the plane of the board. So if you were to take an X-ray crystallographic image of this molecule, you would see 4 chlorine atoms at 90-degree angle to each other. The lone pairs don't show up in in the image. So that's what square pyramidal would look like. Now, for homework, because this is a lot of material I'm throwing at you, at the very least, guys, try to read up to page 357 on chapter 9 of your textbook. Memorize your polyatomic ions. You know, I'm nagging you about this all the time, but it's important. And start reading chapter 9. You can try one thing for homework. I'll give you the answer tomorrow. Page 357, practice exercise. So here's your homework. Page 357, practice exercise. And we'll pick it up tomorrow at the same time and same channel. Hope to see you there.